Hi, welcome back to the channel. Today I'll be looking at the next video in the IB Physics standard level and higher level series, which is C.2, the wave model. I'll be upfront before I begin. It's probably one of the easiest topics in the syllabus, and so it won't take long to cover. And the only things you really need to know are the definitions in this chapter. There's very few calculations, so it'll be quite fast. So basically, traveling waves are just waves that travel, as the name suggests. So they're oscillations that transfer energy but not matter. You can technically say that because they transfer energy, they transfer momentum, but that's not really core to the definition, but it's true. So as you can see, this sound wave from this guitar would be a traveling wave, and so would this wave in the ocean. Both of these are examples of traveling waves. So now let's look at some properties of waves. So waves have a couple properties, and these are listed right over here. So let's go through them one by one. So first is displacement, which is measured in meters, right? So everything here in brackets is the units, the fundamental units. And displacement is how far the wave strays from the starting point. And then we have wavelength. So wavelength is the length of a full cycle. So from here we can see in the photo, the wavelength is the point from here till here. So here we complete a full cycle and then we start a new one. So it's from this point till this point. That's the wavelength. The amplitude is the maximum displacement during a full cycle. So as you can see here, this and this are points of maximum displacements. So would this blue point, this red point, and this red point. So all of them are the amplitude. Conventionally, we usually take the amplitude as positive. So even if it's negative displacement, we just take it as the absolute value, so the positive version of that. And a period is the time taken for a full cycle. So if we imagine that instead of this being displacement, if this axis were time, then the period would actually just be the wavelength. But we have to be very careful here. That would be on a time axis over here and not a direction of travel, so not a displacement axis. And that's measured in seconds. And then we have frequency, which is the number of cycles completed in 1 second. And that's kind of hard to show on the graph, but like if we had an imaginary line, say over here for 1 second, if this were time, that is, and if we have one right over here that's 1 second, then we can see that half a cycle has been completed. So that's frequency, and it's take particular note of the unit here. It's 1/seconds, which we sometimes call hertz, but 1/seconds is fine. So yeah. And then we also have wave speed, which is in meters per second, and this basically defines how fast the wave travels through the medium. So it's quite easy to calculate. All we have to do really is take the displacement of the wave and divide it by the period. And we'll be looking at that more detail on the next slide. So in this topic, there's only really one formula, and that's this one right over here. I've put this just as a refresher. You've probably already seen it in topics like A2 or C1, but yeah, it's just a refresher. Frequency is 1/time, or 1/period, and we use this sort of knowledge to derive the speed formulas. So obviously we know from mechanics that speed is distance over time, and so if we put the sort of physics terms to it, we get that speed is wavelength divided by period, and a wavelength here is the lambda and period is the t. So we have velocity is equal to lambda by t, and now we also know that t is just f is just 1/t. So we can also write this as lambda times 1/t, which is the same as writing it as lambda times f. So both of these are formulas for the velocity of the wave. And yeah, that's pretty much all the calculations you'll need to do. Now let's look at the two types of waves. So there's waves called transverse waves, and these are basically waves in which the oscillations are perpendicular to their direction of motion. That's quite an important definition that you just need to memorize. If it's not entirely clear what that means yet, I'll show it to you a bit later on. But for now, just commit that to memory. So examples of transverse waves are like electromagnetic waves. So anything on the electromagnetic spectrum, like radio waves or ultraviolet, all of those are part of transverse waves. And mechanical waves. So that means like pretty much anything mechanical, like even water waves are mechanical waves. But keep in mind, not all mechanical waves are transverse, just some of them are. And the properties of transverse waves, there's only one important property you need to know, other than the definition. So other than the fact that the oscillations are perpendicular to direction of motion, the other property is that it can travel through a vacuum. So in essence, it can transfer energy without needing to displace itself. And then there are longitudinal waves, and these are basically the opposite of transverse waves. And what they are basically waves in which the oscillation is parallel to the direction of motion, which means that if the particles vibrate in the same direction as the wave travels. And these have two special terms that we need to learn. One is called a rarefaction and the other is called a compression. So a rarefaction is an area of low pressure, and what that means is that the particles move away from each other at this point, and a compression is an area of high pressure, so the particles move towards each other, they're compressed. And yeah, that's pretty much all we need to know for longitudinal waves. Again, if this didn't make much sense, memorize it for now, and I'll go over it a little bit more detail in the next slide. So an example of longitudinal waves are sound waves. So for example, me speaking right now is generating a longitudinal wave because the words I'm saying vibrate with the particles in the air, and they vibrate all the way to my computer's mic, and then that's coming out back to you from YouTube by vibrations that are coming through from your computer through the air and into your ears. So that's how a longitudinal wave works. And also ultrasound waves. So that's like, for instance, you might have heard of an ultrasound scan in medicine. So that sort of thing is also longitudinal. So the property of that is basically that it cannot travel through a vacuum. So like I said, when I'm speaking, the words coming out of my mouth, the wave that's formed by that needs to hit the particles of the air in order to transfer its energy and move back and forth and move towards my computer's mic. But if there were no particles in the air in a vacuum, so if it's like that, then I wouldn't be able to speak or make any sound actually, because then the sound has nowhere to vibrate and transfer energy toward. So that's why longitudinal waves cannot travel through a vacuum. So yeah, here's where I can make it a bit more clear. So I discussed points of rarefaction and compression earlier. If you remember, rarefaction means the particles move away from each other, and compression means they're towards each other, so they're squeezed. So as you can see here in this line, the density of these wave fronts that I've shown here are very close together. So that means this point here is a point of compression, and so is this point, and so is this point. But here they're spread quite far apart, and the same here and the same here. So that's a point of rarefaction. So any points where they're really closely, tightly pushed together is a compression point, and any point where they're far apart from each other is a rarefaction point. So another thing to notice here is that the wave is moving this way. So it's moving from the left to the right, as indicated by this arrow. And the particles in the wave are also moving from the left to the right. So as you can see, these little red dots here, they're vibrating along this axis that it's moving along. So it's in the same direction as the wave. The particles move in the same direction as the wave. And in a transverse wave, it's quite different. So the particles move up and down, but the wave itself is still moving towards the right. So this particle moves like this, but the wave moves like this in a horizontal line to the right. So that's in essence the difference between a longitudinal wave and a transverse wave. Now, just to recap, um, these both are types of traveling waves, and longitudinal waves can travel through a vacuum. Cannot travel through a vacuum. Transverse waves can, and that's the key difference that you need to know between them. So yeah, that's pretty much the entirety of this topic. Now I'd like to show you a exam style question to see if you can do it. So yeah, go ahead and try this question out while for a little second, and then I'll go through the answer. So the question basically says the graph shows the variation with distance of the displacement of the particles in a wave. The frequency of the wave is 600 hertz. What is the speed of the wave? So it might help you to look at this formula right over here and try and solve this question. So I'll give you a second. Alright, so now that you've hopefully looked at the question and tried to solve it, here's the answer. So speed is wavelength times frequency. That's something we established right over here. And if we use that formula, we're given the wavelength is 4 millimeters. So if we take a look here, the time to complete a full cycle is 4 millimeters. And that we can read just by looking at the distance between these two crests, which is 4 millimeters. And the frequency is 600 hertz. That's given by the question. So the speed of this wave is actually 4 millimeters in meters. So we multiply by times 10 to the negative 3, and then multiply that by 600, which gives us 2.4 meters per second. So if you selected option D, then you're correct. I hope you found this video and explanation helpful. So yeah, please do let me know down in the comments below if you have any questions, and see you next time.